Ms. Bergk, the science quirk. Berk, 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 Berk. Ms. Bergk, she makes you work. Berk, 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 Berk. Science is cool. Okay, this is our section 2 of chapter 4, talking about Newton's first law. Newton's first law states that an object at rest remains at rest, and an object in motion will continue in motion with a constant velocity unless the object experiences another external force. So in other words, it's going to continue at a constant speed in a straight line unless there's another force acting upon it. Or when a net external force on an object is 0, the object's acceleration is 0, or the change in the object's velocity. So what is the net force that we're talking about? Newton's first law refers to the net force on an object, and that is the vector sum of all the forces that are acting on that object. And we can find that by using the methods for finding the resultant vectors, like we found in chapter 3. In this case, we're showing a car with the force of gravity pulling down on the car, and the ground expressing a force pushing back up on the car with equal and opposite forces. Also, we have the car is experiencing a forward force and a resistant force between the friction of the tires and the car in the same equal backward direction. Therefore, the sum of all the vectors is 0, so the car is moving at a constant net velocity of 0. Here's a sample problem. Derek leaves his physics book on top of a drafting table that is at an incline of a 35-degree angle. The free body diagram that we see below here is showing the forces acting on the book. And the problem is, find the net force acting on the book. Will it stay in place? Will it slide down the incline? What will happen? Well, we're showing that the table is pushing up on the book, and that is considered the normal force, at 18 newtons. Gravity is pulling down on the book at 22 newtons. And the force of friction acting on the book, which is parallel to the inclined table, is 11 newtons. Now when we set up our problem, we need to define our variables, which we just did, and we need to find our net force. And how do we do that? We have to choose our XY axis. And to do that, I suggest that we line up the XY axis perpendicular to the number of forces that will fall on the most of the forces that will land on the XY axis, and make that our coordinate system. So as you see, we will take the force pushing up from the table up onto the book, that 18 newtons, as our y-axis, and then the friction as our x-axis. So we only have one force to calculate and change the 22 newtons pulling downward and convert those to f of x and f of y, and then add our forces together. So in order to do that, we now need to calculate. We know that our angle of our incline is 35 degrees. Well, what is that in regards to theta right here? Well, we know that a triangle is 180 degrees with its interior angles. We know this angle is 35 because that was given, and we know that this is a right triangle. So therefore, if we subtract those from 180, we'll find that theta is 55 degrees. So now we can find our f of x and our f of y. Our f of x, our cosine of theta, is our f of x over our f of g. And then if we solve for the Fg of x, because that's what we need, the force of gravity in our x direction, we have 22 newtons times the cosine of 55. That gives us 13 newtons going in our x direction. Now we need to find our y direction, and we'll take the sine of theta is f of y over our f of g. And we take 22 newtons times the sine of 55. This should be f of g of y. They made a mistake here. So our f of g of y, that would be this direction right here, is 18 newtons. Now we can do a new diagram showing our 13 newtons on x direction and our 18 newtons, you could also put it this way, on the y direction with our resultant here of 22 newtons. Now we've got 18 newtons up, 18 newtons down, so they cancel each other out. We have 11 newtons to the left, 13 newtons to the right. Our resultant force is going to be 2 newtons downward. Therefore, our book, here's our 2 newtons, our book is actually going to slide downhill. And here's our force on the y-axis of being 0. So finding the net forces shows that the book will slide down with a force of 2 newtons. Inertia is a property of matter. It is the tendency of an object to resist being moved, or if the object is moving, to resist a change in speed or direction. So the larger the mass an object has, the more inertia it has. So that's also Newton's first law is referred to as the law of inertia. Mass, then, is a measure of inertia. Let's watch a visual concept about this.
To illustrate inertia, let's look at a kickball and a bowling ball. The kickball is hollow and has little mass. The bowling ball has a lot of mass. Let's apply a force to the kickball. The kickball has little inertia because of its small mass, so a force will cause it to accelerate rapidly. The bowling ball is very massive. Its large inertia causes it to resist changes in motion.
Equilibrium is the state in which the net force on an object is 0. Objects that are either at rest or moving with constant velocity are said to be in equilibrium. Newton's first law describes objects that are in equilibrium. So to determine whether a body is in equilibrium, find the net force. If the net force is 0, that body is in equilibrium. If there is a net force, a second force must be equal and opposite to this net force. That would, if that was put in play, that would put that body then in equilibrium.